So in the next example in our lesson 2.1, we're asked to identify the net change in the value of a function, f, as the input changes from a to b. So we were evaluating functions previously in this last example, and we determined that when x was replaced with the number 3, we got an output of 13. And when x was replaced with the number -2, we got an output of 8. So 3 is paired with 13, 2 is paired with 8. So if I were to ask you the question, determine the net change from 3 to -2, we would have to take the output that we got from the latter one. So when x was -2, we got an output of 8, and subtract the output that we got from the previous one. So when x was 3, we got 13. So when we take f of b, 8, minus f of a, -13, we get a net change of -5. Now, another way to display, as I mentioned earlier in class today, another way to display the values of a function is to make a table. The table is going to have an input column and it's going to have an output column. And from that table, we can help to determine the domain of the function. Okay, so for instance, we might say, okay, I want you to evaluate the function f for all values of x between 0 and 5, including 0 and 5. So we could substitute 0 in for x, and we'd get 0 squared is 0. We could substitute fractions in for x as well, but I'll do the whole numbers. We could substitute 1 in for x, and 1 squared is 1. Sub 2 in for x, and 2 squared is 4. Sub 3 in for x, and 3 squared is 9, and so on. We are giving you a restricted domain and are asking you to use the values in that restricted region from 0 to 5 to evaluate the output of the function. So that's not going to be at all uncommon. So you'll just pick numbers within that interval and substitute them into the equation to determine what the output values will be. Okay? So if your function is given by an algebraic expression like f of x equals x squared, and the domain is not stated explicitly like it was on the last example from 0 to 5, then what we generally do is we plug in all possible values for x that can be evaluated using that rule. And we're going to find that with some functions, there are some values of x that are not possible. For instance, look at this function f. I can see that the value of my independent variable lies in the denominator of that fraction. Well, we know from our basic understanding of arithmetic that we can never divide by 0. That means in function f that x minus 4 cannot equal 0. So, therefore, the value of x that would make the denominator 0 would be if x were equal to 4. So x cannot equal 4. And therefore, we would say that the domain of x is all values of x such that x is not equal to 4. Okay? In function g, you can't take the square root of a negative number and get a real answer. And therefore, x has to be a number that is 0 or greater. You can take the square root of 0. You can take the square root of any positive number, but you cannot take the square root of a negative number. So we would identify that the domain of that function g is all values of x such that x is 0 or greater. Okay, so let's try that to use that same logic here in example 2. In A, we define function f to be 1 over x squared minus x. we know we cannot divide by 0. Therefore, that expression in the denominator, x squared minus x, cannot equal 0. So, x squared minus x cannot equal 0 if we factor that denominator, like we were reviewing in prerequisite 6. We see that the GCF is x. If you divide each of those terms by x, x squared divided by x is x, and negative x divided by x is 1. So that denominator factors down to x times the quantity, x minus 1. Neither of those factors can equal 0, because if either of them did, we'd be dividing by 0. Therefore, x cannot equal 0, nor can x minus 1 equal 0. And if x cannot equal 0, that is a number that is not a part of our domain. And if x minus 1 cannot equal 0, then x cannot be 1, because 1 minus 1 is 0. So our domain here in function f would be all values of x except for 0 and 1. So we could write it this way, and we read that as x, all values of x such that x cannot equal 0 and x cannot equal 1. We can also write it using interval notation. That would be everything from negative infinity to 0, not including 0, everything from 0 to 1, not including 1 or 0, and everything from 1 to infinity, not including 1. So you notice I use parentheses with all of these values in my restricted domain. I say from negative infinity to 0, not including 0. I say from 0 to 1, not including either endpoint. And I say from 1 to infinity, not including either endpoint. Of course, the infinities and negative infinities always get a parentheses. This symbol here is just union. That means it could be in the interval from negative infinity to 0, or from 0 to 1, or from 1 to 0.